recording. So, like I was saying before I started recording, a mole is just a name for a number, for a specific number. It's called Avogadro's number, named after the scientist who discovered it, and I want to refer you to the TED Ed video. It's 5 minutes. It's really good. We just don't have a lot of time. And it's what's a mole. This is one that I do expect you to memorize only because we use it so frequently. It would slow you down if you have to look it up every time. The number is 6.022 times 10 to the 23rd. This is Avogadro's number. And like most great scientists, he was mocked for this, and then, after he died, people thought it was awesome. It's kind of a theme. So the really cool thing about Avogadro's number is basically it's a conversion factor between atomic mass units and one atom. So atomic mass units is the unit of mass we would use for one atom. And it's a way to convert to grams, right? When you use a balance in your lab, it doesn't read out atomic mass units. It's grams. If you have a scale and you're American, you probably have set it to pounds, but we use the SI unit, the International System Unit, grams, our base unit for mass. What is really cool about this is that we can, instead of counting individual atoms, which are billions upon billions upon billions upon billions in a tiny speck that's barely visible, instead of trying to count atoms, we can weigh things, right? We can use the mass to figure out how many atoms. So that's what's important about this, is that we use the mass in grams to count or calculate the number of atoms. I had a friend who a million years ago worked at a casino, and the old people love those penny slots, right? Well, who wants to count all those pennies? What they do is they weigh them. Instead of counting individual pennies, because that's not worth anyone's time, right? They weigh them, and they can then calculate how many pennies. This is the same thing, and in the TED Ed video, they have a great analogy. When you go to buy meat at the deli counter, you don't say you want 30 slices of chicken. You order by the pound. So kind of the same thing. What's really, really cool about this, so 6.022 times 10 to the 23 equals 1 mole. Just like 12 eggs equals 1 dozen eggs, or 12 tiny baby kittens equals a dozen kittens. This value, 6.02 sextillion or whatever it is, septillion something, I don't know that much Greek, that's a mole of whatever those items are. But we really just use it mainly for atoms or molecules, because most things aren't that small. So our conversion factor is really cool because it allows us to use mass to calculate the number of atoms. And then we can use a chemical reaction to relate the number of atoms in our reactant to atoms in product. And we can actually predict how much we're going to make. So that's where we're going to end today. But for now, let's just take a look at what this means in terms of elements and the periodic table. So on the periodic table, we take a look at hydrogen. So if you take a sample of hydrogen from nature, you have an average mass, a weighted average mass, because of the naturally occurring isotopes we talked about last time. What is really cool is that a mole of hydrogen atoms weighs 1.008 grams. The mole is the conversion factor between atomic mass units and grams. So instead of talking about 1, all I have to do is put a gram on there. And that is 1 mole of hydrogen atoms. This is another way of using the periodic table as a tool. So the mass number with unit grams equals 1 mole of that element's atoms. Let's look at carbon. Most of you are going to go on to organic, so this one's a pretty big deal, right? So one carbon atom has an average mass of 12.01 atomic mass units, but if I slap a gram on there, that's 1 mole of carbon atoms. So if I have some charcoal, which is carbon, and I weigh it, I can tell you how many atoms of carbon, or I can give you a good number of carbon atoms based on the mass. So one thing I want to note, the mass of 1 mole of hydrogen atoms is different than a mole of carbon atoms. Why are they different? What parts of the atoms have mass? The protons and neutrons. So are those the same or different? Right. So because each element's nucleus has a different number of protons and neutrons, which have mass, a mole of those atoms will have a different mass. So we always have to go through the mass of the element. We can't go from grams to atoms. We can't go straight from grams to atoms. We have to go from grams to moles to atoms. So here's what that looks like. Let's say I have 25 grams of carbon. I've got a charcoal briquette. And I need to calculate how many carbon atoms. So first I have to figure out, well, how many grams does 1 mole of carbon atoms weigh? I just look at the mass on the table, 12.01. And then this is a conversion factor. In order to do dimensional analysis, I convert it into a fraction. Diagonal units have to be the same, so I'm going to put grams down here and mole up here. Right? So if I stop now, I would have around 0.5-ish. I get about 2.08 moles of carbon. So now now that I'm in moles of carbon, now I can calculate atoms. So what I need is 1 mole equals Avogadro's number, 6.022 times 10 to the 23rd. In this case, atoms. So this is moles of carbon. Now this conversion is the same for all elements. A mole of anything is this number. It's the mass that's different or unique to each element. Okay, so again, diagonal units have to be the same. 1 mole on the bottom, 6.022 times 10 to the 23rd. Right, that's a lot of atoms. I get about 1.25 times 10 to the 24th atoms of carbon. I don't want to count those. I'm glad I can just weigh it. That's much more convenient. Okay, so let's say I have 6.98 moles of iron, and I'm asked 4 grams. How much does that weigh? I'm doing a reaction. I've calculated that I need 6.98 moles of iron. So I need to figure out what mass that is, because that's how I can experimentally acquire the number I need. So it's just a conversion. So moles of iron, I like to put it over 1. I know that 1 mole is the molar mass with gram as the unit. So I'm going to use that number, 55.85, and the unit is gram for every single element. Okay. And it's pretty heavy, so that's a pretty good amount. I get about 389.8 grams of iron. So that's how much I would weigh out and add to my other reactants to do my reaction. Let's say I have a number of atoms. Let's say I need 2 times 10 to the 19th atoms of cobalt? Well, I'm not going to count them, right? I'm going to weigh them. Well, in order to do that, in order to go from atoms to grams, I have to go through the molar mass of cobalt. So the atomic mass number with the gram after it is called the molar mass. That means the mass of 1 mole of that element's atoms. So I have to go through moles. I have to go through that conversion factor. So 6.022 times 10 to the 23rd atoms. That's 1 mole of atoms. Now that I'm in mole, now I can use the mass. And for cobalt, it's 58.93 grams. So I took the mass from the periodic table and just put the unit of gram after it. I'm going to double check to make sure that my units cancel. They're dividing atoms divided by atoms is 1, just like 5 divided by 5 is 1. So I'm going to go ahead and punch these in. I'm going to do 58.93. And so how this looks, I don't think we've done a multi-step, so let me talk about this for a second. How this looks in my calculator is I multiply all of the top terms together. That's how I do it. There are a couple of different ways you can do it. So that's just times 1, so I'm going to ignore it. 2 second e, that means exponent. So I'm multiplying the numbers across the top. And I only have one number that's not 1 as the denominator, so I'm just going to divide by that one number, which is Avogadro's number. I'm going to put mine in scientific notation. So I get 1.96 times 10 to the minus 3 grams, which is 1.96 milligrams. So this is a conversion I would expect you to be able to do, going from grams to milligrams. Maybe not in your head like I did. That's okay to write it out. Okay, so we've just explored how we can use mass to get the number of atoms, and we use the conversion factor of mole and Avogadro's number.